So nuclear magnetic resonance, or NMR for short, is used in organic chemistry. It's a technique that's used to help find the structures of molecules without actually doing a chemical reaction on them. You don't need to know the details of nuclear magnetic spectroscopy, but you can look in a textbook to find out exactly how it works. But essentially, it's where we take a sample or molecule and we apply a magnetic field to it, and it's surrounded by a source of radio waves with a radio receiver, and this generates an energy change in the nuclei of the atoms, and it's that energy change in the nuclei of the atoms which determines the structure of the molecule, because depending on the environment of the atoms within the molecule, their frequency changes by a certain amount. We'll call that the chemical shift. So the first type of NMR we're going to look at is carbon-13 NMR. So this only works with carbon-13 and not carbon-12. So we know that all organic molecules contain carbon. 99% of the atoms in any sample that contains carbon will be carbon-12, and around about 1% will be carbon-13. However, carbon-13 NMR uses a modern instrument which is very sensitive, and because it's very sensitive, it can detect these carbon-13 atoms in the molecule. So if we had a sample, let's say the sample was methane, for every 100 methane molecules, 99 of the carbon atoms would be carbon-12, and one carbon atom might be carbon-13 in that particular sample. So it's only the carbon-13 atoms that we actually detect in here. So what we get is something called chemical shift. Now, chemical shift is given the symbol delta, like this, and it's measured in units of parts per million, ppm, and we compare that to a zero. So it's chemical shift, shift in frequency from a reference point, and that reference point is defined as zero. And to get that reference point, what we do is we put a standard in there. So we physically put a standard molecule in our sample, and one of the standard molecules that we use is abbreviated to TMS, which stands for tetra methyl silane. And in the next video, we're going to have a look at the structure of this to understand why we use TMS as a standard. But all we need to know in this case is that the TMS is given a value of 0. So the main point about carbon-13 NMR is that carbon atoms in different environments will give different chemical shift values. I'll tell you what I mean by an environment in a second. So different carbon environments give different ppm values, different chemical shift values. So let's have here a picture of a carbon-13 NMR spectra. So this is actually what's produced. Essentially what we get is a graph, and if we have got a graph of ethanol, we would end up with two peaks like this. So a peak here and a peak there. Now it's a strange graph, this one, because 0 is actually at this end here. Now remember, we've got a sample put in there as well. We only put a little bit of sample in, so this peak here was going to be a much smaller, and that is our standard. And along here we have chemical shift. That is measured in parts per million. So if we have a chemical shift here of 15, that will be to do with one carbon environment, and a chemical shift of, let's say, 60 will be another carbon environment. So this chemical shift here at 60 could be down to this carbon, that one there, and this chemical shift here could be down to this carbon environment here. So we can conclude from this graph here, the fact that it's got two peaks, in addition to the TMS standard, that there's two environments, carbon environments in that molecule that are different. This carbon here is different to that carbon there. So there's one example. Now, different carbons have different chemical shifts, and it's to do with the electronegative atom that's in the molecule, which will draw electrons away from the carbons, which shifts the chemical shift a little bit. Now, we don't know the detail behind that, but we do need to know that the different carbons, if they're in different environments, they produce different chemical shifts. Now, luckily we don't have to remember all these chemical shifts, because we get that in our data sheet. So if we have a look at our data sheet, we can see here on the back of our periodic table, we've got various tables. So we know about the infrared. We do that at AS. Again, you'll be using that though in some of your year 13 questions. We've got proton NMR. See, there's a proton there, which I'll cover in the next video. And we've got carbon NMR. So we're looking at carbon NMR now. The thing to notice here is that it's the carbon which is in bold that it refers to. So we can see here we've got a carbon here which is attached to another carbon with 3 bonds to it. This carbon here is attached to a halogen. This carbon here has a carbonyl next to it. This carbon here has got an amine group next to it. This carbon here has a single bond oxygen come from it. So that must be an alcohol, an ether, or an ester. Now, we don't cover what ethers are at A-level, but I'll give you that just because it's written there. It's where you've got a carbon and then an oxygen and then another carbon. That's what you call an ether structure. We know what an ester and alcohol is. You'll have a carbon-oxygen single bond. This structure here is where we've got an alkene. Here is a nitrile. This is to do with a carbon in a benzene ring. And here is the carbon directly bonded to a double bond oxygen. So whereas this one here was the one next to it, this one here is within the bond. However, we've got 2 of these. The top one here is for esters and carboxylic acids. Just says acids there. It does actually mean carboxylic acids. And this one here is for aldehydes and ketones. What I suggest you do, if you haven't already done this, I'd print a copy of this data sheet out and write that information down there. Just rewind the video if you want to and annotate that please on here. We're going to be using this sheet in the next couple of videos quite a bit. Okay, what we're going to do now is we're going to have a look at some more spectra. So if you've got the molecule propanone. Now the mistake that people make here is they count the number of carbons and they think there'll be 3 peaks. However, there are only 2 environments here, because that carbon environment is the same as that carbon environment there. So we have 1 carbon environment here and another one here. There's 2 environments. So for this one, you'd probably see a spectra which looks a little bit like this. You'll have your TMS standard here at 0, and then a peak right down at the bottom here, roughly, let's say, would be right down at the bottom, let's say 30, and another one right up the top here at 200 and something, let's say 205. Now we've got to work out which peak corresponds to each environment here. We use the data sheet for that, remember? So what we're looking for here for environment number 1, well, we're looking for a carbonyl-carbon. So it's not that one, because that is a carbon next to a carbonyl. We're looking for a carbonyl-carbon, so it's either going to be this one or that one. Now we know that it is a ketone, and that's because the value is 205. Now 205 is between those 2 values there. So it can't be an ester or an acid, it must be a ketone. So it's this one here. So this value here is for environment number 1. And so this one must be environment number 2. Let's just check that. So we're looking for a carbon next to a carbonyl-carbon. So that's this one here, a carbon next to a carbonyl-carbon, which must be between 20 and 50, and it's 30. So that's environment number 2. Let's do one more here. So let's have a look at the structure of propanone. Propanal, rather. Propanone, the carbonyl-carbon will be in the centre carbon, but I'm going to put it aside there. This is going to be propanal. So let's have a look at the structure. How many carbon environments are here? Well, this time we've got 3 carbon environments. 1, 2, 3, like that. So the spectrum might look something like this. You'd have your standard tetramethylsilane here at 0. Perhaps another peak right down at the bottom here at, let's say, 5. Another maybe here at 37. And another right up the top at, we're going to say 205 again. Okay, let's identify which peak is which. So let's bring back the data sheet. So let's have a look at peak 205. So it can't really be anything else apart from this one here. So that there would be carbon number 1 here. Remember, carbon number 2 here in the previous example was next to a carbonyl-carbon. And again, we've got a carbon here next to a carbonyl-carbon. And on the data sheet, a carbon next to a carbonyl-carbon. So that would be number 2. And then we've got a carbon here that's next to a carbon. Oh, beg your pardon, wrong one. We've got a carbon here on this one. Carbon here, which is just next to a normal carbon. It's not a carbonyl-carbon with 3 bonds coming from it. So it's just this one here, isn't it? Yeah. and that one has to be 5 parts per million. So it's this one here, that one there. So that one must be carbon number 3. 1, 2, 3. Let's have a look at one more structure. So let's look at the 2 position isomers of propan 1-ol and propan 2-ol. So let's try skeletal this time. So that's propan 1-ol. And that's propan 2-ol. So how many peaks would propan 1-ol have, and how many peaks would propan 2-ol have, and can we suggest some values of those peaks? Well, how many environments has propan 1-ol got, and how many environments has propan 2-ol got? So propan 1-ol has 3 distinct environments. 1, 2, 3. So we'll call that environment number 1, that one number 2, that one number 3. Whereas propan 2-ol has only 2 environments. Let's call that environment A, here and here, and that's environment B. So propan 1-ol has three peaks in its carbon-13 NMR, but propan 2-ol has only 2 peaks in its carbon-13 NMR. Now, this peak here, so this is a peak B, could be bonded to an OH. So let's have a look at our data sheet. Excuse me, and find an OH chemically bonded to carbon. So we've got here CO, which could be an alcohol, or an ester, or an ether. So this would work. So it's going to have a peak, it's somewhere between 50 and 90, let's say 70 for example. Which picking any value between these 2 numbers here. And we have a carbon there, which is represented by A on the diagram. So that is going to be quite a low value. So something like this. So we'll have a carbon here, which is attached to 3 bonds, 3 hydrogens come off there, which is attached to another carbon. So something like this. So the value between them 2 values there, let's say 30. So environment A will be 30 parts per million or thereabouts. Let's do the same thing for this one. So we'll call that environment number 1, remember. So environment number 1, that's an OH, so again 70-ish parts per million. Environment number 2, so here, this environment would be something like 30 parts per million. And then environment 3 would be a slightly different value as well, let's say a little bit more.